Okay, so we've talked about failure of identification, and in this section of the lecture I now want to introduce a framework for causal inference. And this is a mathematical framework that aims to make clear the conditions that are required for identification of causal effects. That's the purpose. So we're talking in this section of the lecture about causal identification. We'll look at estimation later when we cover methods for causal inference. So the aim of the potential outcomes framework is to identify the effects of interventions on outcomes of interest. And the starting point, the underlying philosophy, if you like, is that we're going to focus the identification problem on studying the potential effect of causes rather than deducing the cause of effects. So what does that actually mean? Well, the distinction that's being made here is between associational inference and causal inference. And the argument is that when we conduct associational inference, we start with the outcome of interest, that's Y, and we there try and infer effects on that outcome. So, we've looked at regression models in this course, where we build a model that tries to determine or predict how Y is determined by a number of possible effects. But the starting point is to try and explain why, so to speak. Causal inference takes a different perspective. It starts not with the outcome, but with the effects. And it views the observed outcome as one potential realization caused through manipulation of that effect, where the effect is our intervention of interest. So the idea being that if we'd intervened in some different way, if we'd manipulated the effect differently, then that would have produced a different outcome, or what we're going to call potential outcome. And this concept of manipulation or intervention is key to understanding how potential outcomes framework seeks to achieve identification, because ultimately it's going to try and look at the difference in intervention or manipulation that determines potential outcomes. So the potential outcomes framework then is going to seek to identify the effects of interventions, and our causal inference is going to be generated by contrasting potential outcomes that different interventions could produce. So at this point, I now want to set the notation and terminology that we're going to use to discuss causal inference. We'll adopt the notation that's routinely used in the causal inference literature in this field of statistics, and it differs in some minor ways from that we've seen previously. So for instance, we're not going to use bold to indicate vectors and matrices. That doesn't make a great deal of difference. I just want to be clear that because a symbol is not bold does not mean it cannot be a vector. Let's start with terminology. As I said, causal inference is focusing on interventions, and we're going to use the word treatment to refer to an intervention variable of interest. So the intervention or treatment is regarded as a random variable. In other words, you could be treated or untreated, you could be treated at one level or some other level. So treatment is a random variable. The treatment is the intervention, and as we manipulate the treatment, we give rise to different potential outcomes. And our inference problem is going to use those different potential outcomes to identify a causal treatment effect. That's what we want to find out. What effect does the treatment have on outcomes? Now, notation. We're going to index units as usual by I, and we have n units in the sample. And typically causal inference problems, certainly in the potential outcomes framework, analysis is conducted on a random vector that has 3 elements. So this random vector here, by this type of Z symbol, it's a kind of curly Z symbol, it has 3 elements. Y is the response, that's our usual outcome. D is the treatment, and X is a vector of covariates. So the response Y, nothing to say here because we've seen responses before throughout the course. It could be binary, it could be categorical, it could be continuous. We're not saying anything specific about its distribution. Then we have the treatment variable that I've just described, and we're denoting that by capital D because it's a random variable, indexed by I because it's a treatment for unit I, and it takes values in the set represented by curly D. So it could be binary. taking the value of 0 or 1. It could be categorical, that is multi-valued, or it could be continuous, falling on the real line. Notice that we're using small d to denote specific values. So this is the random variable, capital D, and small d's are fixed values. And the third element of that we're going to use for causal inference is a covariate vector. Note, a vector, we're not going to put these symbols in bold, but this x is not necessarily a single variable, it could be a vector. So actually we have three different types of covariate vectors listed in the slides, but the one that we're going to talk about most, that's most important in causal inference, and the one that we've talked about previously in this lecture, is the vector of confounders. That's given by xi. That's the symbol we're going to use for confounders. And these are random variables which have dependency with both d and y simultaneously, as we've seen before. So the confounders are the most important one in a way, but there's two others I want to mention because they come into play at various points. The second is non-confounders, covariates that have dependency with y, but they don't have dependency with the treatment d. So non-confounders would be found in a regression model for y, but they're not correlated with d. And finally, third, we have instruments which are the opposite of non-confounders. So they do have association with the treatment d, but they do not have association with y. They're independent of the outcome. And we're going to use instruments when we come to the third causal method we'll discuss today, a method known as instrumental variables, based around these special type of covariates. So that's the terminology and notation. I now want to talk about the structure of the causal inference problem and the key to understanding potential outcomes via the concept of treatment assignment. So this concept of treatment assignment is very important. And the idea here is simply that units are assigned to treatment according to some potentially unknown mechanism. And that mechanism determines whether units receive treatment or control in the binary case, or whether they receive treatment small d rather than some other level in the non-binary case. And we use the indicator function shown here to indicate that unit I has been assigned to a fixed level of treatment, in this case treatment level small d. So in this case, the subscript is representing the treatment level that's assigned, and in brackets this tells us that that treatment level d was assigned to the random variable for unit I. So in other words, unit I received treatment level d. Just to press this home, for example in a binary treatment, treatment would be indicated as either using subscript 1 for the treatment received by unit I, or subscript 0. And assignment to one level of another is what's going to give rise to a set of potential outcomes in random variable y. In other words, that's what's going to allow us to define different values or different versions of y for each unit in the sample. So now let's just define what a potential outcome is, and we're defining this at the unit level. For each unit I, we define this quantity here, yi open brackets small d, as the potential outcome for unit I when exposed to treatment level di. So that's just telling us this is what the outcome for unit I would be if they were treated at level d. Now, there are lots of potential levels of treatment. We can treat at level d or lots of other levels, and therefore the full set of potential outcomes for any unit is written here by curly y. And this is the full set of responses that would happen at every dose that we could conceivably think about, every level of the treatment that's possible. In a binary case, of course, that's just treated in control, but in a multi-valued and continuous setting, there could be multiple potential outcomes. There will be multiple potential outcomes. So that's the potential outcomes. That's what we're going to use our framework, or our framework is going to revolve around those quantities. Now, the second important definition concerns what's called stable unit treatment values. And the stable unit treatment value assumption, and that's abbreviated as SUPVA, that we're going to make, that's the assumption we're going to make, and it just sets out the fundamental consistency requirement for observed and potential outcomes. So it shows us how observed outcomes relate to this concept of potential outcomes. And it's really simple. So in the binary case, if a unit is treated, we observe the outcome under treatment, and we don't observe this bit. We don't observe this potential outcome because this is going to equal 0. If the unit is untreated, we observe the potential outcome under control. That is, we observe this bit of the expression here, but we don't observe this bit. So potential outcomes and observed outcomes are consistent. They correspond according to the treatment actually assigned. The observed outcome will equal yi open brackets 1 if the unit's treated. It will equal yi open brackets 0 if the unit is untreated. Now let's look at the multi-valued or continuous case. That's exactly the same thing. The observed value corresponds to the potential outcome conditional on the level of treatment that was actually assigned to the unit. So if the unit receives treatment level small d, then we will observe in the data, our actual observed data will show the potential outcome at small d. So just establishing consistency and showing how observed and potential outcomes equate. Now together, these two definitions give rise to what is known as the fundamental identification problem of causal inference. Because we don't observe all potential outcomes at many different treatments. For any unit, we observe the actual outcome, not the set of full potential outcomes. So for instance, for a binary treatment, we observe exactly 50% of the potential outcomes. If we observe a unit treated, we will never observe it controlled. If we observe a unit controlled, we will never observe it treated. And that's because these two outcomes are mutually exclusive. We never observe the joint density of both of these outcomes at the same time. Similarly, for multi-valued or continuous treatments, we observe less than 50% of the potential outcomes. We only observe the level actually assigned in the data. So that's the fundamental identification problem. It'd be nice to have all these potential outcomes and compare them. If we did observe that, that would be identified, but they're not. But in the potential outcomes framework, we're still going to imagine that those potential outcomes exist and could have happened under a different treatment regime, and therefore that they're relevant for inference. And in fact, what we're essentially going to do in the potential outcomes framework is we're going to view our causal inference problem as a missing data problem. That is, we observe only outcomes that are realized, not the counterfactual outcomes, so we have missing data. So then, our aim then is to say we want to compare the outcome actually observed with other potential outcomes that we would have observed had the treatment taken a different level, but we've got an identification problem. Not only do we have an identification problem, but furthermore, complicating matters further, the treatment assignment mechanism, which we do not necessarily observe, determines missingness. That is, it determines which data values are observed and which we don't observe. And if that mechanism has some systematic patterns to it, then we're going to have systematic patterns to our missingness. And that's going to cause us an inferential problem. In fact, it's going to cause confounding as the fundamental problem that we have to deal with, and I'll demonstrate that in a minute. But before I do that, we first need to define targets of inference, or what we call estimands, the causal estimands. And these are the quantities that we're actually going to try and identify, even though we have a fundamental identification problem facing us. So in the potential outcomes framework, there are many causal estimands that are used routinely, but there's three that I want to look at which are important to us and which are commonly the target of inference. The first one is called the individual causal effect, or the ICE. Now ideally, if there wasn't a missing data problem, we would establish how changes in treatment induce changes in Y for the same unit. And this is called the individual causal effect, and it's defined here as the difference simply between two potential outcomes for unit I. So notice that the tau is the symbol that we use for the treatment effect. It's indexed by I because it's specific to unit I, and it's simply the difference between the potential outcome unit I would have recorded under treatment level D minus the potential outcome under treatment level 0, or in other words, under control. This doesn't have to be control, it doesn't have to be no treatment. It could be some other reference case, but we'll use control for the moment just to keep matters simple. So that's the individual causal effect, but it should be immediately obvious that due to the fundamental identification problem of causal inference, this isn't identified because we're never going to observe these two outcomes either side of the minus sign. But it turns out that instead, if we focus our identification problem on average causal effects, then under certain conditions we can achieve identification even with the fundamental identification problem of causal inference. And these two estimands are known to be the ones we're interested in, the two average causal effects, so averaged over the whole sample, actually population causal effects, and they're defined as follows. First we have what's called the average potential outcome. So the average potential outcome is given by this symbol here, mu d. It's not indexed by I because it's an average or an expectation over the population. That's important. And this causal effect is simply the expected outcome in the population if all units in the sample had been treated at level small d, fixed value d. Now again, we don't observe all of these potential outcomes. We don't observe all units in the sample treated at that level. We know that, but unlike the individual causal effect, what I'm going to show is it turns out that if we're prepared to make some assumptions and give some structure to the causal inference problem, then we can identify this estimand under certain conditions. The second causal estimand we're going to talk about is called the average treatment effect. It's again an average over the population, and it's just the difference between two average potential outcomes. So it's the difference in average potential outcome, this quantity here, evaluated at fixed level small d, and the difference between average potential outcome evaluated at some other reference value, in this case at no treatment or control, treatment level 0. So it's the difference in expected outcomes for all units in the population at treatment level small d relative to treatment level control. And again, note that this is a population average that we're specifying because we've got an expectation defined over the sample. So that's all very well. We've got our estimands, or two average estimands, but how do we go about achieving identification of these average causal effects? Well, the potential outcomes framework is going to establish the conditions under which the average potential outcome and the ATE, the average treatment effect, can be identified in the presence of confounding. And actually, it's confounding that's causing a failure of identification for average treatment effects, and this relates to the material we covered previously in the lecture. And in the causal inference framework, the way that we understand the problem of confounding is to focus on the treatment assignment mechanism that I said was important earlier. And we're going to look at what that implies for missingness. That is, for the idea that potential outcomes are missing, we end up observing some, but not others. And what does confounding imply for that process of missingness? And the way to think about this is to contrast randomized and unrandomized treatment assignment, which we've done here in this diagram that I'll come to in a minute. Because for our inferential purposes, a randomized treatment assignment corresponds to one that is unconfounded, and I'll explain that in a minute, and an unrandomized treatment corresponds to one that is confounded. And that's because confounding and the nature of treatment assignment mechanism are very, very closely related. So here we have two DAGs for the standard kind of causal setup with three elements to the data, that is y, d, and x. On the left hand side we have a randomized assignment represented, and left hand side randomized, and on the right hand side we have an unrandomized assignment represented. And you can see straight away that this diagram here is confounded, and this one is, as we'll discuss, unconfounded. So let's start with the left hand side randomized assignment. Under experimental conditions, if we randomized, we could randomly assign treatment across units. And if we did this, this would give unconditional independence between the potential outcomes that we would observe and the treatment assignment. And this is written in this form here. So this says that the potential outcomes at level D are independent of assignment to level D for all doses that we might want to consider. So what does this mean? This is saying that the potential outcome is independent in the way that I've just said of the way the treatment has been assigned, or in other words, the potential outcomes are independent of the assignment mechanism that produces the value of D rather than some other value. Now this can be quite confusing when you first see it. What this is not saying is that treatment is not associated with outcome under randomization. We know that it is associated with outcome as shown in this part of the DAG because we had to have a direct causal path from D to Y. What this is saying instead is that the treatment assignment itself, that is the mechanism that determines whether unit I gets assigned to treatment or control or to some level of the treatment, is independent of the outcomes that we observe. And the key to understanding this is the process of randomization. Now, it must be the case that treatment assignment and outcomes are independent as long as the treatment assignment mechanism is random. And that follows simply because randomization implies there's nothing systematic in the assignment to cause any association. There's no common factor X, if things are randomized, that ties D and Y together, and that's really the important point. There isn't confounding. There can't be as long as things are randomized, because we randomized over X, the characteristics of a unit, and therefore it cannot be correlated with D, and as long as it's not correlated with D, there is no backdoor path. So under randomization then, any unit in the sample is just as likely as any other to receive a particular level of the treatment, and that means that there's no common factor, there's no backdoor path that allows us to get from D to Y, and that is why unconditional independence holds. If there was a backdoor path, unconditional independence would not hold, because the value that the outcomes take would be dependent on the treatment assignment mechanism via the path that can be taken through X. So actually the absence of confounding, that is, the absence of a common factor and association, arises due to randomization, and that is why there is a very close link between randomization and the concept of confounding. Now conversely, when we observe confounding, that's typically due to a non-randomized or unrandomized treatment assignment, and this will hopefully become clearer and easier to grasp once I give an example of when unconditional independence doesn't hold. But first of all, I just want to explain why, if unconditional independence holds, we can identify the average treatment effects under this condition. And this is shown in this simple proof here. So this is just saying that random treatment assignment applies unconditional independence, which is this condition here. It takes this form. This allows us to identify average treatment effects as follows. So this is just the definition of unconditional independence here. And we're assuming that this holds. This is our estimand, which is the average potential outcome. Because unconditional independence holds, we can condition this expression on the indicator variable, and it makes no difference because of this property here. But once we've conditioned on the indicator variable, then that tells us that unit I has received treatment level small d, so we can then use SUTVA, the stable unit treatment value assumption, to replace the potential outcome with the actual outcome, and we have identification here in observable data. And once we have that identification, that justifies estimation of this this causal quantity, this potential outcome, and the average treatment effect simply by our sample means. So on this side we have a sample mean of, or a subsample if you like, of the units that receive treatment level D minus a subsample mean of the units that receive treatment level 0. We take the difference, and this gives us a consistent estimate of the average treatment effect. And the fact that it's consistent is simply justified by a law of large numbers. Okay, that was for a randomized treatment. Now let's turn to unrandomized, and this is the right hand side DAG shown here. In this case, treatments are assigned via a mechanism that in this case you can see is determined by X. So X is determining what value of D is assigned to each unit. And that means that we've got this backdoor path, the confounding backdoor path that we've talked about previously. And that's how, unrandomized assignment relates to confounding. The confounding immediately implies that this condition cannot hold due to the fact that there's a backdoor path that means the y's are not independent of d simply by virtue of the fact that x, that common factor, ties them together. So x is relevant for the treatment levels received by each unit, and it's also relevant, that is d, it's also relevant for the outcomes because it affects y, and that's what the confounding is happening. That's what causes confounding. And that means that under randomization, counterfactual outcomes are missing at random, while under unrandomized assignment, that leads to systematic missingness, and the systematicness, if you like, being determined by the confounding factors x, and that's really what's causing the problem. So unrandomized essentially meaning confounded in this setting. So let's have a look at a concrete example that I hope will make this clear. And in this example, we want to estimate the effect that speed cameras have on road traffic collisions across a sample of treated and untreated links. So a treated link being one that has a speed camera, and an untreated link being one that does not. But in reality, speed cameras are assigned disproportionately to high flow, high speed and large capacity routes. And that means the assignment is certainly not random. It's systematically determined by a set of covariates that we're going to call as x, capacity, speed and flow. And capacity, speed and flow in turn have a direct effect on collisions. So they have a positive effect on collisions in the sense that higher capacity, higher speeds and higher flow are going to lead to a higher number of accidents. So we clearly have a backdoor path in this case, an indirect path, not causal actually, but necessarily causal I should say. So in the absence of any treatment, even if we didn't assign a treatment, we would still expect the average collisions in the treated group to differ from the average for the control group due to differences in their background characteristics, x, that influence collisions. Or in other words, because x positively affects y, we expect more collisions to happen in the treated group regardless of the causal effect of speed cameras. Places that get speed cameras tend to have higher capacity, higher speed, higher flow, and places with higher speed, higher capacity and higher flow tend to have higher collisions in any case. So D and Y are associated even without a causal effect of the treatment, although there is one in this case due to the backdoor path. And I hope that demonstrates the principle that in this situation the potential outcomes are not independent of treatment assignment unconditionally, and therefore if we use this kind of approach for identification, we will not identify the true average treatment effect of speed cameras. So what can we do? Well, actually the solution is very simple. If we cannot invoke unconditional independence because we have some amount of confounding, then all we need to do is invoke a conditional independence assumption, which we're going to call the CIA, the conditional independence assumption. That's what we're going to evoke to achieve conditional independence, but it's going to be conditional on confounding covariates x. So here is the assumption. It's called the conditional independence assumption. And as stated here, it says the potential outcomes for unit I are conditionally independent of treatment assignment given a sufficient set of observed confounding covariates. Notice that this is now a conditional independence. It's conditioned on x. And importantly, we're talking here about conditioning on confounding. We don't care about other covariates that might appear in the model for y or d. We only need to condition on confounders. So what we're saying is that y is independent of treatment assignment if I take into account the problem of confounding that the x's are causing. Or in other words, it's independent conditional on x. Yeah, conditional on confounding covariates x. So it's really just as simple as this condition in x. And if x is sufficient to represent confounding characteristics, then that gives us independence conditional on x, and we can use that for identification. So the CIA then essentially states that dependence between treatment assignment and outcomes is nullified conditional on x. Just take x out of the problem by conditioning, and as long as the x vector that we're conditioning on provides a sufficient representation of confounding for the conditional independence assumption to hold, then in effect what we're doing is we're mimicking the assignment that would arise under randomization by conditioning on x, and we're replacing the unconditional assumption with this one here. And if we can do that, then I'm going to show you that we can identify average potential outcomes and average treatment effects even when we have confounding and even when we have the fundamental identification problem of causal inference. And this theorem here states that very simply. So under conditional independence, the population average treatment effect and the population average potential outcome can be identified by conditioning on x and integrating over the covariate distribution. So this is the S-demand of interest, the average treatment effect, that we want to identify. We condition this expression on x, and we integrate over x, integrate over the distribution of x. So this is just an iterated expectation, as we saw in lecture 1. There's nothing new here. It's the expectation of the average treatment effect conditioned on x, but with x integrated out, so we get back to this quantity here that's not conditioned. We then use the conditional independence assumption and SUPVA, the stable unit treatment value, to first condition on assignment and to replace the potential outcomes with the actual outcomes, and we have identification then given this expression here because we're now dealing with data that can be observed. And this gives us our expression for the average treatment effect here. So population average potential outcomes and therefore average treatment effects are expressed as expectations over the confounding covariates x. By integrating out of that distribution, we get the average causal effect. And then just to finish in this section, that's really covered what I wanted to say. Just to finish in this section, the last slide shows the steps, derives the steps just for a little proof of how the average potential outcome and the average treatment effect in the first case are identified under conditional independence for the binary and multi-valued continuous cases. So let's start with the average treatment effect in the binary case. This is just stating the S-demand, tau 1, average treatment effect for a binary treatment. We condition on x and we take the expectation over x. This is simply an iterated expectation. We use the conditional independence assumption to condition on treatment assignment, and we use SUPVA to replace potential outcomes with observed, and then we have an expression here for the average treatment effect in observable data for the ATE, and therefore it's identified. Similarly, for a continuous or multi-valued dose, that is small d, this is the average potential outcome we're looking at. Exactly the same process. This is our S-demand. Use iterated expectations to condition on x and take the expectation over x. Use the CIA to condition on treatment assignment, and then finally use SUPVA, the stable unit treatment value assumption, to replace potential outcomes with observed values, and again we have identification. So what this section has shown then under the potential outcomes framework is that average causal effects, the population APOs and ATE, can be identified. In the unconfounded setting, they can be identified just by using sample means due to unconditional independence, and in the confounded setting, they can be identified by using the conditional independence assumption along with the SUPVA.